Welcome back to another functions and applications lesson where today we're looking at domain and range. So our learning goal today is to use set notation to express the domain and range of different quadratic functions. So if you remember, we have two variables, independent and dependent variables. So x is our independent variable, which is also our input into a function. And y, which is our dependent variable, is the output, and its value depends on x. So if you remember what a function is and how we looked at a machine, so the input values are going in a machine, and something happens to all of them to get that output machine. So all of those output values are dependent on the input value. So now domain and range pretty much refer to all the possible values of our independent and dependent variables. So domain is the set of all values for the independent variable, whereas range is the set of all possible values for the dependent variable or the output. And what we use is set notation, and that's pretty much a way of writing numbers as a set. So we have the curly brackets, and all our numbers are separated by commas. And here we have a pattern of even numbers. So we can see that 2, 4, 6, 8. And the three dots just tells us that this will continue on for all the positive even numbers. So this is the set of even numbers. Now, we also will be using a new notation, which is the set of all real numbers. And how we write this in a handwritten form, we draw a little rectangle and the R. So it's a bold R or like a solid R. And this is pretty much all our possible real numbers. So decimals, fractions, positive, negative numbers, rational, irrational numbers, all. In my text, you might see this R or this R. They both mean the set of real numbers. I will use them interchangeably. So if the variable x is a real number, so our input value, then we can say that x is part of the real number set. So x belongs, this E here means belongs, to the set of real numbers. And in our examples, we'll see that this will always be true. So our set notation will always start with that. Now we will add a condition. So if our variable x is a real number, it can only have values greater than 3. We write that x is part of the real numbers with the condition. So that straight line means conditional on x being greater than 3. So all values greater than 3. Had I told you that it's all values of x equal to or greater than 3, with that equality, we just add the equality there, and it's the same thing. Or if I told you it's all values of x less than 3, we would just write it as less than 3. So let's look at a couple examples here where we're just looking at linear functions for now. So the first function is f of x is negative 3x plus 4. So if you remember plotting a linear function, you can try that right now, but it will be approximately something like, I have to do a little bit more. Hold on. Let me do it this way because it'll go kind of like this. Or here. This is f of x. So for a linear line, we know that any value of x that I put into the function f of x is going to give me an output value. It will just multiply that value by negative 3 and add 4 to it. So any x value will be true here. So my domain is going to be, and I'm going to start writing now just with set notation, but x belonging to R, and that's it. It has no conditions on it because x can be all values. Similarly, I hope you know that when we write these arrows, it means that our line is extending infinitely upwards and downwards, which means that eventually we will also hit all values of y, which is our output value. So y can actually be all the real numbers as well. And a question for you now would be, would this hold true for all linear functions? And you should have got that yes, it will, because for any linear function, x can be any value, and you can choose x however way you want to get all values of y as well. So it'll be both belonging just to the set of real numbers with no condition. Now, the only exception will come when we have linear functions that are horizontal or vertical lines. So let's take a look now. We have our first one, which is y equals 5. So if I have 5 here, I would have a straight line going like this. So in this example here as well, the domain could be all real numbers, right? I can choose any x value and y equals 5 will hold. That being said though, my range is only one value and it's 5. Whatever x I choose, my machine doesn't care. It will just give me 5. So I do have a condition here where y is in the real numbers and y is equal to 5. You can have that as a condition as well. So I'm just saying that any value of x will give me y equals 5. And that works. And I'll briefly show you if we have a vertical line now. Let's say something like this. So keep in mind, this is not a function based on our definition of function because at the given point x, we have all the possible values of y. So it does not fit our vertical line test for it is a vertical line. That being said, we can write its domain and range. So here, I see that based on a vertical line, y belongs to the set of real numbers, and we will get all values of y since it's a vertical line. So that's my range. And now for my domain, I see that, for example, let's say this was 3. X can be in the or is in the set of real numbers, but it can only be equal to 3. At any point on this vertical line, x will have a value of 3. Similar to how in the horizontal line, at any value of x, we have that y is equal to 5. So that's where we get those two special cases for domain and range within linear equations or linear in these two cases, a linear function, but in all of them, a linear equation. So now let's move on to our first quadratic example. So here you are asked to find the domain and range of y equals 3x squared minus 12x plus 15. And you're asked to graph using methods from Unit 1. So at this point, you might have graphed it using a graphing tool like Desmos, or I did a table of values and plotted my 5 points. And now I'm just going to draw my parabola as best as I can. And so our domain and range here, let's do some analysis. X can be any value in the real numbers. So I can put any value into, and remember y is also f of x, into this function, and it will give me some output value. It will hold true. So for my domain, x is the set of all real numbers, and that's it. Now for y, I see that almost any input value will give me a lot of options for y. However, we have a minimum here, and our minimum is at 0.23. So while my x values can be any x as I go from right to left, my y values can only be anything above 2. However, it can be 2 itself. So we will write range as y belongs to a set of real numbers, and y is greater than or equal to 2. And so for any quadratic function, you're going to see parabolas. So your parabola might be like that. It might be like going this way. It could be like this way. So When you're looking for the domain and range, your x value will be the real numbers in all cases. However, you have to keep in mind the range might have a restriction. And for that, we look at the maximum and minimum values to determine what possible values are there for y. Is y always greater than a certain value or less than a certain value? So here, same thing now, just with written. So we can just fill this in. Uh, X is my set of real numbers, but because of that vertex, we have our range as Y is in the set of real numbers, but Y is greater than or equal to 2. Oh, my bad. 3, 3. I've been using 2, but it's 3. If you caught that earlier, well done. Okay, it's greater than 3. So now let's look at these next two examples. At this point, I think you're familiar enough to try and pause to try these on your own. So take a moment to do that and then come back and check your answers. So for this first example, it is a straight line and it is a linear function. So at this point, oh, we would have domain. X is all the real numbers and our range right here is Y. Oh, is in the set of real numbers. And that would be it. Now, for this one, we have two restrictions here. I am limited from X on two sides and from Y on two sides. So here we're going to see a domain and range is going to look a little different than the ones we've seen so far. So domain here, we still have X is in the real numbers and Y is in the real numbers. So always starting with that. And now our restrictions. So our X value starts at -4 here and goes to 10. So my X has to be between -4 and 10. And for Y, we have our minimum here at -7 and our maximum here at 7. So -7 and 7. And there we have it for that one as well. So just some key ideas. So in a horizontal line, the range is just the value of y. So you're going to have that y equals. And same with a vertical line, we have our domain as x equal to something, which would be the value of the straight line. And for quadratic functions, we do have the set of real numbers as the domain, but the range does depend on the vertex. So first check where your vertex is, whether it's a minimum or maximum, and that will help you determine the range. So now let's look at a word problem where we're told a flare is shot vertically upward and its motion or a motion sensor records its motion as it moves up, and it kind of goes like a motion up and down, similar to a quadratic model. And so here we have the table of values and we're given the height every 0.2 seconds. And we are also told the function here is, let me highlight that, h of t is equal to -5t squared plus 10t. So the height is in meters and our time is in seconds. And we could have figured that from the table of values as well. That always is a little cheat sheet for our units if it's already provided for you. So now we're asked, how does the motion of the flare affect the domain and range of the quadratic function? So with all of these application problems where you have an object moving through the air, we always want to consider two things. The starting point, is the object above the ground, or does it start from above the ground, or is it shot from the ground and has kind of like a motion like this? Also, as the object is moving through the air, the object reaches a maximum height and then it goes back down until it reaches the ground. So This movement will give us a restriction for both the domain and the range. With real world applications, although the parabola will continue beyond based on the equation h of t, we want to interpret the domain and range within the problem. So for an object moving through the air, I only care about the time while the object is in the air. So starting from the time that it is launched until it lands back on the ground. And in terms of its height, I only care about the height where after, again, it's in the air, the maximum height it reaches, and then the time it goes back down to the ground. So that's what we have over here. The time of the flare is going to be our domain, so our x-axis or our independent variable, and our dependent variable is the height, which changes based on the time, and that will determine our range along with the maximum height. So in this example here, I've already provided the domain for you. So we have, and here because we're using t, you're going to switch to t. We're not using x because our problem uses t. So t is in the set of real numbers with the restriction that we are only considering t between 0 and 2 because that's the time where my flare is in the air and the equal is when it lands. And that's when we have the t equals 0 and t equals 2. And the range can be written as, and see here now, I will write it as h of t for that function because I'm saying that the values of this function are in R, but I only care about the values of the height within 0 and 5 inclusive, which, if we look at the table of values, at 5 is the maximum height of that flare. And again, we have the inclusive symbols there. So we're saying that we only care when it starts from the land at height 0, reaches the maximum height, and then lands back at height 0. So looking at the graph here, can you confirm the domain and range using this graph? So we see here that yes, we go from 0 to 2 here, which is that t value. And so if we are looking at the motion up and then it goes back down, those t values hold. And same with our height, we reach our maximum height of 5, and then we reach back down at 0. And how can you interpret the results? We've already pretty much done that, but now try explaining it using this graph now. Specifically include points. We start at time 0, at height 0, and it moves to a maximum height of 5 at time 1 second until it reaches the ground again at time 2 seconds. And that's our final example for this lesson as well. So for today, please practice some of the vocabulary we saw as well as some examples of domain and range using the graphs. So some of these are not functions, but remember with the vertical line test, you do not need it to be a function to determine the domain and range. You will still be able to find the domain and range. You will just have restrictions on it. So please keep those restrictions in mind. And as well as a table of values. So lots of practice from everything today, and I'll see you all next class for another lesson on domain and range with more application-based questions.